So some additional aspects of waves and electromagnetic radiation specifically that we should discuss are interference and diffraction patterns. Now it turns out that some of the properties of one of the properties of any waves, and of course electromagnetic radiation in particular, is that it undergoes something called interference. And that is, if the maxima of two waves traveling close together, if the maxima are perfectly lined up, as well as the minima, if they are said to be in phase, what happens is they will undergo constructive interference, and the amplitude of their individual waves will sum and of course increase in intensity. Okay? If we think about the particle nature of light, this should make sense. If you have two waves propagating in the same direction, they're in phase, and say this wave is 5 photons and this wave is 5 photons, it will appear as a light source traveling with 10 photons, twice the amplitude. The other side of the coin is if the waves are traveling out of phase, meaning that the maxima and minima are lined up, these waves are out of phase. And what happens is when these two waves come together and they're out of phase, they undergo destructive interference. What happens here is their waves cancel each other out. This is exactly this phenomenon is actually used in technologies used today, of course, noise canceling headphones. So if you've ever used them, what noise canceling headphones try to do is try to reduce background noise that you experience. Okay, so any sound, which of course is a wave that you hear, has a specific wavelength and amplitude, and what the noise canceling headphones do is they detect the wave that you would normally hear and produce a wave that is perfectly out of phase, or as close to that as possible. And what happens is those waves cancel out and it reduces the noise that you hear through destructive interference. Okay. Another property of waves are diffraction. And now what happens in diffraction is that as a wave passes through a barrier, which has a opening right here, pictured here, what will happen is the wave will propagate through the medium, or what we call diffract, to expand to the medium. Okay, particles do not do this, of course. If particles are sent through a barrier, the particles that do go through the slit will go through, but they won't propagate throughout the medium. They won't spread out as waves do. Okay. A real-world example of this would be, of course, if you're standing outside of a building and you yell. Of course, sound is a wave, and someone standing not directly through the opening of that room will still hear you, because the sound waves will propagate and diffract through the room. So even if that person isn't directly in this line of sight, as it would be, of the sound waves, they would still be able to hear you. Of course, that does not happen for particles. If you throw a tennis ball through a door, there's no way that it's going to curve around and hit someone that's not directly in line with that slit. Okay. One of the experiments, or one experiment that you can do is or view interference is by passing a wave through a double slit opening, two openings inside of a barrier. Okay, so what happens is, of course, these waves will propagate or travel to that barrier, and the waves that go through the two slits will start to diffract or spread out to fill the medium. Now, as they diffract through the medium, if you put a sort of photographic film or detector, the two waves will travel different distances to reach the same point for that detector. And what that produces is a very systematic pattern of both destructive and constructive interference, where the waves that are out of phase will undergo destructive interference and create a dark spot where you don't see any light, and waves that can undergo constructive interference will produce a bright spot on that detector, and which we would call that as a diffraction pattern. Okay. Well, it turns out that these same experiments, this double slit experiments that was done for many years using light and of course other forms of waves, was also carried out with electrons, which up until this point we've always thought of as particles. They have a mass, they have a charge. We can think about knowing their position in an orbital. They are or behave as particles. So if we submit a source of electrons to a double slit opening, we would expect to see just two bright spots in a detector where the particles, which don't diffract, hit the detector. They're only going to go through that slit, travel the distance to the detector, and you would see two bright spots where the electrons lining up with those slits would hit. It turns out that very, very, very surprisingly, the actual electron behavior caused a interference pattern, meaning that the electrons passing through these two slits underwent both constructive interference and destructive interference to produce bright spots and dark spots, indicating that electrons act as both a wave and as a particle. So just like the photon, the electron has a wave-particle duality to its nature. So if the electron can act as a wave, it turns out that we can detect or calculate a wavelength of electron. And of course, by extension, all matter, anything that has a mass, does have a wavelength. Electrons, because they're so light, gives them an appreciable or measurable observable wavelength. Objects on the macroscopic scale, large molecules, people, do not have, although they do have a wavelength, very small, hard to detect. Okay, so this calculation was developed by a French physicist, de Broglie, and if you divide the mass and the velocity of the electron by Planck's constant, you will get the wavelength of the electron. Okay, so let's do an example of that. Okay, if we have an electron traveling at 2.65 times 10 to the 6th meters per second, we can calculate, if we know the velocity, we can calculate the wavelength. So we've got de Broglie's wavelength equation, h over the mass times the velocity. Notice that is v, velocity, not frequency, nu. Okay, and we've got 6.626 times 10 to the negative 34th joules seconds. We know that h has units of joules seconds. But it turns out that if we look at the unit for joule, which is a derived unit, we can use its fundamental units, which is kilograms meters squared per second squared. Those are the, above all, the fundamental units of a joule. So that will help us determine what our unit should be for our final answer. Okay, kilograms meters squared per second squared divided by the mass of the electron, which we learned previously when we discussed subatomic particles, was 9.1 times 10 to the negative 31st kilograms. And the velocity is stated here, 2.65 times 10 to the 6th meters per second. And you can see that kilograms is going to cancel out. One of these meters is going to cancel out. Of course, this was joules second, so there's another second there from here. 1 second cancels out here, and then 1 second cancels out here. So we're left with just units of meters. So the wavelength of this electron is, throw all this into your calculator, and get a value of 2.6 times 10 to the negative 10th meters, or 26 nanometers. So on the order approaching the visible light spectrum of electromagnetic radiation. Okay, so one of the biggest conclusions or product of realizing that the electron has the wave-particle duality, it turns out that it made it a lot more difficult to determine properties of the electron, and actually led to a new form of physics known as quantum mechanics. Because of the particle wave duality of matter, and as well as, again, that energy, light, became quantized, led to sort of a new paradigm shift in physics known as quantum mechanics. And one of the biggest outcomes of quantum mechanics in our journey to discuss properties of electrons was the uncertainty principle, which was proposed by Werner Heisenberg, another German physicist. And here's the equation for the uncertainty principle. But really, it all it can be boiled down to that the fact that we cannot know the position. We cannot know the exact position of electron and its velocity or speed to 100% certainty. And actually, it turns out that the greater accuracy we know the position, the less accurate we know the speed or velocity, and vice versa. The more and more accurate information you have about its velocity, the less and less accurate information you have about its position. Okay? So from this uncertainty principle, instead of a true classical mechanics approach to position and velocity, such as the classical trajectory of, say, a baseball thrown from the pitcher's mound to the catcher, we can calculate its velocity and position with 100% certainty using classical mechanics or Newtonian mechanics. It turns out that because of these new fundamental properties of the electrons, we are going to have to switch to a quantum mechanical probability approach to knowledge and information about the electron. So if the electron is going to travel from point A to point B, all we can do is determine its probability. Okay? If we sort of do calculations, theoretical works, we'll get information about where it could be. Okay? And if you look at this sort of shaded plot, all of these dots would be individual calculations about where the electron could be in its trajectory. Now, it turns out that there's a higher probability of it being in the center, less probability as you go above or below that trajectory, but again, it's all based on probability. And this is really going to transform our discussion of the electron within an atom.